Welcome to Have You Read It? The channel where we bring books to life, one summary at a time. Today we're diving deep into Quantum Supremacy, How the Quantum Computer Revolution Will Change Everything, by Michio Kaku. This book isn't just about faster computers. It's about a paradigm shift that could redefine technology, medicine, and even our understanding of the universe. Prepare for a journey into the mind-bending realm of quantum mechanics and its potential to reshape our future. Kaku kicks things off by establishing the central premise: quantum supremacy is no longer a distant dream. He cites announcements from Google and the Chinese Academy of Sciences, where quantum computers perform specific calculations that would take even the most powerful supercomputers thousands, or even trillions of years to complete. This marks a turning point, signaling the dawn of a new era of computation. It's important to grasp that quantum computers aren't simply faster versions of our existing machines, Kaku emphasizes. They operate on entirely different principles, enabling them to solve problems currently intractable for classical computers, regardless of processing time. The book points out that a mouse trapped in a maze may have to tediously analyze each path, one by one, on a digital computer, where a quantum computer simultaneously analyzes all possible paths at the same time. The script notes the intense global race to develop practical quantum computers, with major players like Google, Microsoft, IBM, and others vying for dominance. These companies recognize that quantum computing could be the most important computing technology of this century. The public is getting a taste, with some companies offering access to their early-stage quantum computers via the internet. The IBM Q experience, for example, allows users to experiment with quantum computation firsthand. The intersection of finance and quantum technology is underscored by the fact that IonQ became the first major quantum computing company to go public, and startups like PsiQuantum are valued in the billions. Kaku highlights the economic implications, citing estimates that the quantum computing market could reach tens of billions of dollars within a decade. Recognizing the importance of this technology, governments are also investing heavily, exemplified by the U.S. National Quantum Initiative Act, while acknowledging the rapid progress. The script also mentions a crucial caveat: quantum computers capable of solving real-world problems are still years away. Some critics even question whether they will ever live up to the hype. Regardless, tech companies recognize the importance of establishing a foothold in this emerging field. The narrative shifts to explaining the impending end of Moore's law, the exponential growth in computing power driven by the shrinking size of transistors on silicon chips is approaching its physical limits. As transistors shrink to the scale of a few atoms, quantum effects become significant, hindering their performance. This sets the stage for quantum computers, which exploit the laws of quantum mechanics to overcome the limitations of classical computing. Qubits, unlike classical bits, can exist in a superposition of states, both 0 and 1 simultaneously, vastly increasing the amount of information and computational power that can be processed. This allows quantum computers to analyze all possible solutions to a problem simultaneously. The phenomenon of entanglement further enhances the quantum computer's power. When qubits are entangled, they become interconnected, and their fates are intertwined, no matter how far apart they are. This allows quantum computers to manipulate information in a fundamentally different way than classical computers. One of the key challenges is maintaining the delicate quantum state of qubits, which are susceptible to decoherence due to environmental noise and disturbances. Scientists use extreme cooling to minimize decoherence, but finding ways to maintain coherence at higher temperatures remains a major area of research. The podcast outlines several potentially revolutionary applications of quantum computing, including the ability to improve search engines, optimization processes, and molecular simulations. Quantum computers can quickly find the key factors to optimize problems in search and data analysis, which would allow them to analyze a company's finances, predict the future of certain markets, minimize expenses, and maximize efficiency. The unique optimization capabilities of quantum computers could revolutionize various industries, including finance, logistics, and materials science. Kaku notes that the combination of AI with quantum computers could exponentially accelerate learning and have profound effects on medicine and biology. The script emphasizes simulation as a crucial application. Quantum computers may simulate the aerodynamics of planes to reduce friction. Governments might use them to predict global warming, and scientists may use them to find configurations of magnets in fusion machines. Within medicine, pharmaceutical companies could set up virtual laboratories to analyze the effects of drugs. All of biology, medicine, and chemistry would be reduced to quantum mechanics. Quantum computers have the power to address climate change by modeling the interaction of molecules for carbon capture and producing super batteries, which could revolutionize the environment. For food production, quantum computers may be used to unlock the secret of nitrogen fixing to create a second green revolution, and to help scientists create a more efficient synthetic photosynthesis, or perhaps entirely new ways of capturing the power of sunlight. In the context of medicine, not only can quantum computers simultaneously analyze the efficacy of millions of potential drugs faster than any conventional computer, but they can also unravel the nature of disease itself. They can create new vaccines and therapies to help combat different diseases. The focus shifts to reintroducing the Antikythera mechanism, which represented the beginning of computer technology. The quantum computer may represent the highest stage in its evolution. The podcast explores attempts to improve computers, such as that of Charles Babbage, who tried to build the most advanced mechanical computer to plot everything from the planets to ships at sea. As a founding member of the Royal Astronomical Society, he had an interest in tracking the planets and astronomical bodies. He was also concerned with producing accurate navigational charts for the maritime industry. Ada Lovelace was also a key figure, as she is now known for being the world's first programmer. Lovelace wrote that the computer could be programmed to create musical pieces. The computer could be used to explore science, art, music, and culture as well. The narrative transitions to pure mathematics and whether mathematics is complete. Kurt Gödel proved it was impossible to list all true statements in mathematics when given a set of axioms. 2,000 years of Greek thinking was completely and irrevocably shattered. The podcast script transitions to the work of Alan Turing, who framed computer science. In 1936, he introduced the concept of the universal Turing machine. All of modern society is built on Turing machines, such as the giant supercomputers or the cell phone in your pocket. With a Turing machine, one can perform any operation involving addition, subtraction, and multiplication. During World War II, Turing was recruited to perform top-secret work at the British military installation at Bletchley Park. There they were tasked with decoding secret Nazi codes. The work of Turing and others replaced the analog computer with a digital computer. Because digital messages can be copied over and over again and lose hardly any information with each cycle, digital computers can be vastly more accurate than analog computers. Colossus was finished in 1944, in time for the final invasion of Normandy, which the Nazis did not adequately prepare for. This sealed the fate of the Nazi Empire. His accomplishments were kept classified for decades, so no one knew of his contribution to the war effort. After the war, Turing returned to artificial intelligence and the question, can machines think? He replaced endless philosophical debate with the Turing test, a simple reproducible test to which there is a simple yes or no answer. His work was then cut short because of social issues related to his homosexuality. The script turns to quantum physics, starting with Max Planck, who made the assumption that the energy emitted from an atom could only be found in tiny discrete packs of energy, which are called quanta. To do the calculation, he had to introduce a number representing the size of the quantum of energy, h, which was an incredibly small number. He proposed his idea cautiously, diplomatically claiming that if you introduce this trick of packets of energy as an exercise, then you can precisely reproduce the actual energy curve found in nature. Einstein made a big leap in his work related to quanta. Light could act like a particle, the photon, or a wave, as in optics. Somehow, light had two possible forms. Then, Schrödinger created the wave equation to describe the motion of these particles. But what was controversial about quantum mechanics was the fact that a wave has to finally collapse and give the correct answer. One cannot know which state the electron is in until a measurement is made. This is called the measurement problem. Einstein would say, God does not play dice with the universe. It was this artificial separation between the macro world and the micro world that scientists most objected to. Finally, the podcast host addresses Einstein and his concerns about quantum entanglement. In this view, if you measure the spin of one electron and find it is spinning clockwise, then you instantly know that its partner on the other side of the galaxy must be spinning counterclockwise. The host mentions the tragedy that affected physicists during World War II, particularly with members of the quantum community. The host also addresses the coming of a new quantum invention, the transistor. John Bardeen, Walter Brattain, and William Shockley created a revolutionary device by using semiconductors, setting in motion the computer age. Richard Feynman was a visionary. In fact, the next frontier for physics could be to create machines as small as atoms, pioneering a growing field now called nanotechnology. Feynman then introduced one of the most amazing ideas, path integrals, which states that when an electron moves between 2 points, it sums over all possible paths connecting these 2 points. Decades after Schrödinger introduced his wave equation by magic, with no derivation, Feynman was able to unify the entirety of quantum mechanics, including the Schrödinger equation, using this path integral approach. This helped solve the problem of coherence in warm environments. David Deutsch took these mind-boggling concepts seriously. He asked why quantum computers were so powerful. He then claimed that electrons are simultaneously calculating in parallel universes. Deutsch then developed the idea that, in Everett's many worlds theory, the electron is a point particle that indeed went through just one hole. But there was another twin electron in a parallel universe that went through the other hole. The chapter summarizes the bizarre features of the quantum theory, including superposition, entanglement, the sum over paths, and tunneling. Then Shor's algorithm is discussed, which was the first algorithm that showed the security risk involved with the next stage of computers. In the summary of the final sections, the conversation switches to greening the world, medicine, and quantum computing. Many areas are now on the forefront of this exciting new age, and quantum physics can be extremely useful in many ways. Several aspects of the green revolution are now taking place. The energy, environment, and climate have now become something that all different types of business have made their focus. This allows companies to start to change the rules and invest their money and time into fixing the problem of carbon outputs, which will hopefully lead to fewer disasters from the world of science. In the world of medicine, it might also be possible to change the ways that illnesses spread and the different steps to treat cancer, or ALS. It is known that some new treatments have actually come from the world of quantum mechanics. The liquid biopsies are becoming quite accurate and a good source for those to use who need different treatments. New research is showing us how to help in a variety of areas and may be a way of improving things for the future. The next steps involve understanding what is happening. The most important point is that in this quantum computer revolution, scientists may be able to bring much of their technology together to make the quality of life improve for different people. The conversation then switches to whether you can be immortal and use this quantum method to live long. One may be able to live for 1,000 years, if a way was able to be found to reverse time and to look at where life is headed. The laws of thermodynamics seem to go against it, because what can be done with a life form would result in what causes the problems that are being thought through. The goal for each person may be to use everything we find in these new laws and what they can do for our lives. For a time frame, what it can give you is a way of looking for a solution. A scientist's dream is that in a generation there can be ways of figuring out if there would be side effects. In short, there are several different scientific aspects to take into consideration with the world and where we are going. It then jumps to a hypothetical scene in 2050 when quantum computers are fully realized. Then, in the distant future, we will be able to explore different parts of the world, even where the meaning of the universe will finally be at our fingertips. Turning to quantum puzzles. The channel host then focuses on the larger issue of what was all done to change aspects of the world through computers. To discuss these quantum computers in the world, quantum mechanics, and also how things can be improved. The future must take into consideration that perhaps quantum physics may allow for a better view on it. Quantum physics must see how to improve by using computers to take the process into account. The universe may also make our journey different in many areas. With a little work, you will also divide space and time. With a lot of potential, there is room to grow and use what you learn from them. The main takeaway from the book, Quantum Supremacy, is the transformative potential of quantum computing and the realization that we are on the cusp of a technological revolution that could reshape various aspects of our lives and understanding of the universe. Here are a few easy-to-remember heuristics inspired by Michio Kaku's book that can help keep in mind the information discussed in this book. Moore's law is slowing, quantum is growing. Remember that while classical computing advancements are hitting a wall, quantum computing is rapidly developing, offering solutions to previously intractable problems. Qubits greater than bits. Understand that qubits are exponentially more powerful than classical bits due to their ability to exist in multiple states simultaneously and become entangled with each other. Quantum computing is not just speed. Keep in mind that quantum computers aren't just faster. They can solve problems digital computers can never solve, even with infinite time. The universe is a computer. Consider that the universe itself operates according to quantum mechanical principles. And quantum computers may one day help us unlock its deepest secrets. Quantum computing in all areas. Remember that it also might be the answer that we need in all areas of science. Thanks for watching. Make sure to give this video a thumbs up and hit that subscribe button so you never miss our next book dive.